Alright, welcome back to some more physics lectures. Today's topics are going to be nuclear and quantum physics. So the last lecture we got into the sort of basic ideas or what led to kind of this revolution that became about in the early 20th century that we now understand as quantum physics, sometimes just called quantum mechanics, all that quantum stuff. And so we're going to talk some more about that and then get a little bit into some nuclear physics, though just like with a lot of other topics we've gone through, we're really only going to get to skim the surface. So kind of just throw out some ideas for you, and that'll have to be about it for now. Okay, so let's just recap real quick our lessons from the photon. Right? So from the light quanta lecture, we basically found that photons can act like particles or they can act like waves. They do both. And that brought about this whole idea of that wave-particle duality and just having to kind of accept that things that seem contradictory are actually not contradictory. In the end, they're complementary. They actually can work together. And secondly, I kind of threw this out at the end, or maybe quickly at the end of the last lecture, about how thinking about where a photon is in any given time and where it's going to land at any given time kind of leads us to the idea that the universe operates fundamentally on probabilities. It's not a deterministic sort of picture. You don't just go one step to the next step and say, oh, this is how it got from exactly from here to here to here, this is exactly what's going to happen afterwards. We can say very well, in most cases, or a lot of cases, what will happen, because the probability is incredibly high that it will happen. But when it comes to the world of the very, very small, sometimes we call it the quantum world or subatomic world, things are inherently probabilistic, and so you can't determine beforehand what actually will be the outcome of any given circumstance. Okay, so the last lecture and the last few lectures were all about light, and it was light that really led people to understand the nature of this quantum world and how it varies it's very different than how we usually interact with on our sort of normal scales, like human scales. Also would call that kind of more normal interaction is oftentimes in physics now called classical, because it relates to sort of pre-era, classic sort of period of physics. So, as it turns out, it's not just photons that behave as particles and waves, or can act as either one. I think in 1924, this guy, De Broglie, I don't know how to say his name exactly, but he essentially proposed that all matter and all particles, all subatomic stuff, all the things that make up the universe, actually have this wave-particle duality as well. They all can act like particles, and they can all act like waves. It's not just photons. Right? So it's electrons, protons, neutrons, other things we haven't talked about, muons, neutrinos, quarks, gluons. There are all kinds of stuff at the subatomic level that we're not really going to be able to get into. But they all have this property where they can either act like a particle or act like a wave. And most of those things were essentially thought of as being particles. Electrons, protons, they were all basically understood as being like billiard balls, things that were just like flying around, knocking into other things. What De Broglie kind of gave us was that, well, they can also act like waves, meaning that they also have a wavelength associated with them, they have a frequency associated with them, they have things, they can form interference patterns with other particles like them, because that's all the things that waves do. And as it turned out, it only took a few years until experiments were designed and conducted to basically prove him correct. He was right. That if you perform essentially like the double slit experiment we went through with photons, if you perform essentially the same experiment with electrons, you see the same pattern, or you see the same result, which is an interference pattern. Right? So that was essentially that electrons are traveling like waves as they go through that double slit experiment, just like the photons do. And then furthermore, more and more experiments were done to kind of look at this sort of idea and whether or not it was true, and it's just continually been proven to be true. Everything acts on the quantum scale, the subatomic scale, everything acts as a particle and it acts as a wave. It just depends on sort of how you look at it and what the circumstances are. So this term matter wave is used just to indicate essentially that all matter, things, and remember matter is a term that means something that has mass, so I could say it has a kilogram or a gram or something that has mass. That's matter, but all matter actually acts like waves just as photons do. And the pictures here are actually sort of microscopic images, actually using a special kind of microscope, an electron scanning microscope, I believe. But what they are is basically rings or different shapes of atoms, maybe like iron atoms. So all the kind of fenced areas, like the different geometric shapes, those are larger subatomic entities, like an iron atom, say. And researchers are able to actually put them on a surface in a particular pattern, like a triangle or a square or a circle. And what ends up happening is the electrons that are on that surface, it's usually a metallic surface, so there's kind of electrons that are free to move around the surface. When you place all of these atoms around and kind of make this corral, what you get in the middle are these waves, these standing waves. And those waves are the electrons that are corralled in the center, and they're interfering with each other to form these standing waves. So these pictures are essentially pictures of electrons acting as waves. Okay, so that brings us to, well, essentially the question of how best to describe these matter waves. If all of these things at the subatomic scale are acting like particles or acting like waves, we need a way to describe them. And it actually was this guy, Schrödinger, who formulated an equation, which was essentially what we call a wave equation. But it's a wave equation to describe matter waves. And we don't look at a whole lot of equations in this course, but it's such a famous equation that I figured maybe you should see it. And essentially what it's, this version of the equation, there are a number of different versions or ways to write it essentially. Essentially this is saying that on one side, the energy that a matter wave has is equal or can tell you how it is going to evolve in time. The right side is sort of how it evolves in time. So you don't really have to understand any of the things that go into that, but it's nice to actually at least see it at some point. The important thing here is this idea of a quantity or a thing that we can use that essentially stands for, say, an electron or any kind of subatomic particle. That thing needs to have, well, if we want to be able to make predictions about what it's going to do, or basically to make predictions and to see if our predictions are true, then we need to have a thing that's going to describe that. And that thing in the Schrödinger equation is known as the wave function. So psi, that little like trident looking thing, is a Greek letter, psi, but in this case it is the symbol we use for the wave function. Right? So the wave function is that thing that essentially stands for the electron or the atom, or it doesn't have to be just a single subatomic thing, it can be a collection of subatomic things, but it's like the thing that's we're actually doing the description of, say, the electron. And what it can tell you about it is basically what is possible for, again, say an electron, what's possible for an electron to do in a given scenario, and how probable or how possible is it for you to find it doing any of those things. So a lot of confusing or maybe sort of abstract ideas there. A decent analogy, though not a perfect analogy, is to imagine the wave function of a poker game would essentially tell you or describe all the different hands that are possible in a poker game and how possible it is that you're going to be dealt any of those hands at a given time. So it's a very abstract idea, but the thing that it is, it's just what is able to describe subatomic entities. So one area where the kind of evolution of this idea of matter and photons and all different stuff as being either like a wave or like a particle and then like both and then like either, one of the places where that evolution really played out was in understanding the atomic spectra of different elements. And so the atomic spectra is essentially just the light that different elements will give off after you sort of energize them in a way. Like you pump a bunch of energy into them and then they start to give off light as photons. And if they were giving off, you know, a whole wide spectrum of light, like the whole visible spectrum, then essentially we'd get, you know, you'd energize the element and then a full like white light would come off, and that white light would be made up of all these different kinds of things, right? Full spectrum of visible light. Turns out that's not the case, and that almost is never the case for any particular element. So instead what happens is, again, you have to kind of give a bunch of energy to that element, and usually the elements are in a gas form of some kind. So in this picture here, it's sort of like a neon gas tube, or it doesn't have to be neon. In the picture, it's actually hydrogen. But you have a tube that's filled with hydrogen gas, and you essentially pass a bunch of current through it so that you dump a bunch of energy into that gas. And then out of that gas then comes light. And the light, if you pass it through a prism, remember prisms can do this diffraction thing, and particularly in a prism they diffract and they spread out light so that you actually see the different kind of components that make up that. So what was found, and was known for quite a long time, is if you do that with hydrogen, then you essentially get these 4 main wavelengths of light that are coming out. So it's only really like 4 different kinds of photons that are coming out. There are these different wavelengths, kind of hard to read on the screen right here, but one's like 413 nanometers, one's 430 something nanometers, one way up here is at 600 and something else nanometers. And so those are, you know, there's some blue, one bluish, one violetish, one reddish, somewhere in the middle, a cyan of some kind. But that was it, right? At least right here, that's all the wavelengths that you would see coming off of this hydrogen. So this is what you would call the atomic spectra of hydrogen. And you could do that for other things. I believe that one is neon, and neon has a lot more wavelengths that it puts out. Iron, again, has even more wavelengths that it'll put out, but each of these are unique sets of wavelengths that the elements will put out. And yeah, so there are only certain wavelengths, and those wavelengths depend on the kind of gas that it is. So they depend on the element you're actually looking at the light coming off of. Okay, so one of the ways, or one of the, I guess some of the earlier and still rather successful ways of describing this spectrum, this atomic spectrum, or spectra, was known as the Bohr model, because it was thought of by Niels Bohr, the guy I mentioned last time too. And essentially what he said, or his idea, his theory, was that electrons that are orbiting around the nucleus of an atom, so remember an atom is going to be made up of a nucleus, and the nucleus has protons and neutrons inside, and there's electrons that are somewhere orbiting around the nucleus. So it's sort of like this very simple diagram, this very simple picture up here. And essentially what he said is that the electrons can only occupy what we would call stationary states. So there's only certain sort of orbits or distances that electrons can be at around the nucleus. And they can't exist in between those. So when an electron moves from one state to another, say from this outer state down to this inner state, or this inner orbit, stationary orbit, then it's going to give off a certain photon associated with the jump between those two. And well, the picture in the bottom left here is showing the spectrum of hydrogen, and it's showing it as basically it comes from electrons jumping from further and further orbits down to this sort of closest orbit to the nucleus. So in a sense, this is a very classical-ish model where it just thinks about the atom as being sort of like a solar system, and electrons are like planets orbiting around the sun in our solar system. And when an atom is going to emit light, basically that's like a planet that jumps from one orbit down to another one. And the larger that jump is, the more energy is given off. So larger jump, more energy is a higher frequency photon given off. So yeah. You would label some of these states with numbers like n. N goes, say, 1, 2, 3, 4, 5, 6. And if you have, say, an electron in the third orbit, and it drops down to the second orbit, it's not a very big drop, it's not a very high energy. So a longer wavelength, that's about the 600 nanometer photon that's going to be given off. Versus jump from the sixth orbit all the way down to that second one. That's a much larger jump, much higher energy, much shorter wavelength. That's going to correspond to that furthest over one, that 412 or 13 nanometer. So Bohr's model is essentially there's like fixed spaces, rings, these orbits around the nucleus, and electrons can only jump in between those things, and that's why the spacing of those things will determine the energy and the wavelength of the photon that is given off when an electron jumps from one to the other. So this is why atoms and elements, they all have different spacings in their orbits essentially, and that dictates, or that is essentially why the atomic spectra for these atoms are different. All right, so Bohr's model gives us a pretty good idea of why, or somewhat of an idea of why the atomic spectra are the way they are, why there's only certain wavelengths of light that come out, and because those have to do with the fact that there's only certain orbits that are available for electrons to be in any given atom. To get a better understanding, or go kind of even deeper, we then have to take the concept again of electrons acting as waves. So again, all things at the subatomic level can act as particles, they can act as waves. Right? So if we imagine that electrons are acting as waves, then we can get an even better idea of why this is the case. And really it comes down to the same sort of idea of why you can only have certain frequencies or tones or sounds that, like, say, a guitar will make. So if you take like a string on a guitar, it's a certain length, and if you pluck it, one of the things it can do is the whole string can sort of move up and down. Right? That would be like this first sort of standing wave being pictured right at the top here. So you have the whole wave just kind of going, right? That's one frequency that string can do. It could also do any sort of multiple of that wavelength. So if you double that wavelength, then you can actually have this sort of frequency going on, where the standing wave is such that there's actually two bumps, right? It comes up and down and up, right? So it's constantly bumping up and down in two places. Right? Or you could have 3 times that original wavelength and you get this third sort of harmonic. Or you could have 4 times, you get this fourth harmonic. Right? Those are all allowed because essentially each of them is able to be tied down at either end. Because that's sort of just what restricts the string on the guitar. It's just held at either end. Then you could imagine that there's actually wavelengths that aren't allowed on a guitar. One of them might be like this one, where it's sort of like that first wavelength that we saw here, the first frequency it could make, but the wavelength's a little bit longer. So this is sort of a possible oscillation you can imagine, a possible way that string could move, except for it's forbidden because it doesn't actually stop or have this sort of stationary point right where the string ends. So you can't have that. It won't. Your guitar just can't do that. Similarly, you could imagine taking one of those wavelengths and shortening it, and then again, we have what you would say maybe is a forbidden wavelength there, forbidden frequency, because it doesn't follow the physical constraint that the string needs to be tied down and not move at these 2 points, at the 2 ends. All these other ones are examples of frequencies that can happen. They all stop at these particular points, so they don't move at those points. These ones do. So for a guitar, there's allowed frequencies, there's these allowed standing waves, and there's also these forbidden ones. There's all kinds of examples, more examples of both. These are just some. So the same idea then we could think holds for electrons. Right? So if electrons are waves, then you can imagine that it has a certain wavelength, and the restriction for it to be around an atom, for it to exist in an orbit around an atom, is that wavelength essentially has to meet up on itself. If you took that wavelength and you wrapped it around, you need the 2 ends of the wave to always meet up. I guess maybe in this bottom left picture is an example where you could imagine taking, say, a wave that's gone through, I think it looks like 5 oscillations. It's gone through 5 sort of wavelengths. But if you bend it all the way back around on itself, it both meet up at this sort of peak of the wave. So in a sense, they're still meeting up, even though you're kind of taking this wave and you're bending it around back on itself, but it's meeting up at the same point, essentially, as it started on, right? Where it started, it's kind of finishing there, so you can pull it back around. Well, so that would be an allowed standing wave here. This other picture is a forbidden one, where when you take that wave and you try to wrap it back around on this circle, on this distance here, you wrap it back around, the waves are doing different things when they meet back up, right? Like one's going up, one's going down. And then finally in the picture in the far bottom left here, you can imagine, all right, well, we could get particular orbits, and they're constrained because you have, say, the distance for one electron wavelength, right? That's the shortest distance we can get, and you take that distance and you wrap it around essentially the nucleus, and that's the size of the orbit. You take 2, you allow it's actually think about allowing the electron to go through sort of 2 wavelengths, right? Then you have that double, second one down here. You could wrap that one around the nucleus, and now you have this second sort of orbit state, right? Or it could be 3 wavelengths that the electron goes through, and you could wrap that around the nucleus. So this idea of electrons acting as waves really starts to give you more of a fundamental understanding of why there are only certain orbits around the nucleus where electron can be. Because in between there, the electron wave would not meet back up on itself, and that's, again, it's sort of like trying to get the guitar to do a frequency that's just not allowed. So, as I've tried to emphasize, these ideas can give us an understanding of why the atomic spectra is the way that it is, or why why atoms and elements will emit certain photons of light and not emit other ones. It turns out that if you think about that process in the opposite direction, where instead of an electron jumping from an outer orbit to an inner orbit, giving off a photon, you could have a photon come in and sort of knock an electron up from a lower orbit to a higher orbit. That is a process of absorption. But they're essentially just inverse processes. They're fundamentally work in the same way. And the fact that we now can say that there are only particular orbits, and those orbits are restricted by the fact that the electron wave needs to wrap around on itself and meet up properly on itself, tells us why there's only those specific wavelengths of photons that are given off. And also, like I was saying, for absorption, it's why elements will only absorb certain photon wavelengths too. Because you need to essentially boost the electron up to another multiple wavelength. So just some terminology. When a photon is absorbed by an atom, like I've been saying, you're kind of knocking the electron into a higher orbit. The technical term would be you're exciting the electron. And then once the electron at some point later is going to want to fall back into that lower orbit, do that quantum jump back into the lower orbit, you'd say that's a de-excitation of the electron. And that's when a photon of that same wavelength will be given off. It doesn't have to be the exact same process. So say, like in this picture, you might be boosting an electron or exciting an electron from the second orbit to the third orbit. Right? When it absorbs that photon from the far left, it could fall back down into the second orbit and give off the same wavelength photon. It could also fall back or fall all the way into the first orbit, which would be a bigger jump. So you'd be giving off more energy in that photon. You have a higher frequency photon giving off. So the picture on the left here is sort of another way to imagine those orbits, and it's sort of like jumping up and down stairs. So if I jump down one stair at a time, I'm essentially moving with the same amount, or I'm jumping the same amount of energy at a time, and so each of those jumps would give off the same frequency of light. However, I could also jump over one step. I do like 2 steps at a time. That's more energy in one jump, so you give off a higher frequency photon, and again, higher frequency, shorter wavelength. So, Bohr gave us this idea of this sort of kind of solar system picture of the atom, where you have these orbits, and there's only particular stationary sort of orbits that electrons can exist in. We take that and add the fact that an electron can act like a wave, then we sort of understand why those particular orbits are like that. You need those electron waves to wrap back around and meet up. So that was good, and it gives us good understanding. However, if you really want to get to the actual, or much closer to the actual properties and how atoms actually act and what they look like, and particularly if you want to get a 3-dimensional picture as well, then we need to use that Schrodinger equation that I was telling you about. Basically, like Bohr and de Broglie kind of were taking in these lessons of the photon, or understanding those ideas of quantum mechanics, the Schrodinger equation really sort of takes those to heart much more, and utilizes that equation and the idea of a wave function to actually give you a full 3-dimensional picture of an atom and the electrons acting as waves. And instead of just getting these sort of stationary orbits, like planetary orbits, it then ends up giving you these sort of 3-dimensional pictures, which we call orbitals. Yeah. I think I have another slide on orbitals. Oh yeah, the only other thing to say then is, instead of being just these, understanding them before, like we had orbits that these electrons could be in, when we move also to orbitals, we've taken this idea that probability is a fundamental aspect of the universe, and the orbitals aren't exactly telling you where the electron is, it's sort of giving you a spread, or giving you a place where you could find those electrons. That's why they're sometimes called probability clouds. It's like it's a probabilistic region where it's like, you might have this 50% chance you're going to spot the electron in that region. Right, so the orbitals, well, before I say anything else, there's a picture of just some basic orbitals, and they're labeled in a number of different ways, but partly by this sort of lettering scheme, S, P, D, and I think F and G, and then they go alphabetical. I don't know why. There's some historical reason why it's a weird ordering of letters like that. But anyway, in the picture on the left here that's showing some different examples of orbitals, the simplest one is basically a sphere. It's a sphere, and that it's saying essentially that where the electron's going to be around the nucleus is sort of spherical, the probability you'll find it on one side versus the other side is basically the same as long as you're the same distance away from the nucleus. And it's also spherical in the sense that you move away in a spherical sort of like bubble. The probability that you're going to find the electron further and further out gets less and less and less. So these orbitals they give us a three-dimensional picture, but again, it's not a literal picture to say that this is what the electron looks like or this is what the atom looks like. It's giving you a probability cloud sort of saying where you're probably going to find the electron. So the simplest one again is like a sphere, basically. The next simplest one is basically a sphere within another shell. So instead of just having a one orbit or orbital, you have one orbital and then you have a second orbital around that one. And these are regions where you could find the electrons sitting in. Another example of one is this sort of dumbbell shape, right, the P2 one. And that's essentially where you have these sort of like two dumbbells on either side of the nucleus, and you can find the electron in either of those sort of orbitals. And they just get kind of more and more complex. Like the one that 3D or D3 one is you have these dumbbells, but then you also have this ring around. So those are examples of some orbitals. And it turns out that understanding the orbitals is basically what amounts to understanding the physical structure of an element, like what physical form it takes, the geometry of it. And these SPD labels are used in chemistry. I mean, they're also used in physics, but in chemistry, if you've ever taken a chemistry course, you'll have at some point probably run into having to talk about the particular form of that element, and it has these SPD sort of labels there. It also turns out that now understanding what the physical structure of them looks like allows us to better understand how chemical bondings will happen and why chemical bondings will happen. Because, well, essentially the chemical bondings are just overlapping orbitals. So if you take two orbital pictures and you start to push them together and overlap, like these, the first one is just these two very simple spherical orbitals, you start to push them together and you get a picture of a molecule, right? Two atoms bonded together, where it's now this sort of like figure eight almost shape. And you can get more and more complex bindings given more and more complex initial orbital states. All right, so I feel like I should say this at some point. These are ideas that are probably fairly complex, and I'm not expecting that you're going to be an expert on any of these things. So don't be worried too much if a lot of this maybe is going over your head, or you don't feel like it's hitting very hard. That's okay. At this point of the course, we're dealing with a lot of things that are difficult to get across on a conceptual level. So really I'm just trying to give you an idea, again, of what they are and very basic sort of stuff. So all that said, something that kind of comes up, or you might start to think about at some point, is, okay, we now have this idea of the quantum world, the subatomic world, and things are very different on the subatomic world than they are on our scale, maybe called like the macro scale, or the classical scale. And there could be an issue if there's no way that those two regions sort of meet up. The reason sort of being is that, we have a lot of things on our scale that we understand very well, right? How basically all the stuff that we did for the first 3/4 of this course was macro scale, like classical sort of physics, and all of that works really well for our scale. So there could be an issue if our understanding of that scale doesn't ever meet up with the quantum scale, or the quantum world, or how we understand quantum physics. So I think it was actually Bohr did a lot of stuff in development of quantum physics, but who really pushed this idea of the correspondence principle, meaning that whenever you kind of try to push these two theories into regions where they overlap or where they're going to meet up, then they better agree. Because if not, you just have a complete disconnect between these two worlds, and you might as well be talking about something else entirely. So you can state it in a lot of different ways, but I think one of the ways he stated it was, for a new theory to be valid, it must account for verified results of the old theory. It's another way of saying the same sort of thing. Quantum physics, it's great, it explains some of these crazy things that we're seeing at the very small scale, and very weird sort of phenomenon, but at some point it also needs to be able to explain things that we already understand very well, right? Why does an apple drop when I let it go? So one of the biggest or most straightforward examples of where this needs to be the case or where this needs to happen is, like I've been saying, is the transition from very, very small things to very, very large things. Right? And again, there are other sort of ways of getting to a quantum sort of system than just being very, very small, but that's sort of the easiest one to picture. Quantum physics, again, is a probabilistic theory. It just tells you how likely something is to happen. What kind of things are possible and how likely those things are to happen. And where you actually get it meeting up with larger scale things, sort of macro scale things, the reason that they're able to correspond, the reason that they can meet up, is because essentially the probability that quantum mechanics is going to, or quantum physics is going to give to you, basically tells you that only one thing is really possible at that point. Right? Like if I chop an apple, there actually is a possibility, or if I release an apple, there is actually some possibility that it doesn't fall down, it actually moves upward. It just turns out that that possibility is unbelievably small because of how big the object is, right? And it might not seem big, but when we're talking about the difference between our scale and the quantum scale, the subatomic scale, it's unbelievably big. So when you get to this scale of very, very large things, the only possible outcome is the classical sort of outcome, the outcome we already knew about. Right, so a great way to understand how this switch from this probabilistic things, you know, all kinds of possibilities can happen, to this, well, only one possible thing is really going to happen. How you can understand how that kind of switch might happen, or where that transition might happen. We can think just about flipping coins. So, right, so if you flip a coin, you could ask, well, how likely is it that I get heads? Or how likely is it that I get tails? And if you start with one coin, flip one coin, how likely do I get tails? It's pretty likely, right? It's actually 50%. You have a 50% chance. But if you then say, okay, take two coins, flip two coins, how likely is it that I get two heads? Less likely. Turns out it's only about 25%, or it's 25%. Right? So less likely. If you flip 100 coins, right, how likely is it that you're going to get all heads? Well, at that point, it becomes pretty darn unlikely. Right? It's still possible. And if you do that, flip 100 coins a whole bunch of times, then maybe you will get all heads eventually. But if you take 1 billion coins, or 1 trillion coins, or just outrageous numbers of coins, flip them and ask what's the probability I'm going to get all of them to be tails, it's basically impossible. It's practically impossible. It's not going to happen. You can flip 1 billion coins as many times as you want, you're never going to get all tails. Even though it's still technically possible, there is a possibility that will happen, it's practically impossible. So this is the idea where essentially you're going from this very, very small scale where a lot of things might be possible to you build up a bunch of those small scale things, and you have so many of them, all kind of those probabilities working together, where you get to this large enough scale where essentially only one thing is ever really possible, right? Like I let go of the apple, it falls down. It doesn't fall up, it doesn't fall to the side, it doesn't fall towards me, it falls down. All right, so now we're going to switch gears just a little bit and go towards nuclear physics. Right. In the late 19th century, almost 20th century, this guy, Becquerel, again, I'm bad with pronouncing names, so sorry. But basically he discovered that there were these invisible rays and they were emanating or coming from uranium salts. And he found that they could penetrate through different materials, but was able to determine that they weren't light rays. It wasn't any form of light. And later, or kind of spurred by that, a number of people, but particularly the Curies, Pierre and Marie Curie, did more experiments and did some more searching for other materials that would emanate or give off these same sorts of rays. And they actually found some. The Curies did this polonium and radium, and they emitted these similar kind of rays. So they weren't really sure what they were. They knew they weren't light, and they knew they could kind of go through materials and hit other materials afterwards. So as it turns out, there were a number of different kinds of things that were happening in those processes. They're all talked about or labeled, put underneath the category of radioactivity. And essentially, radioactivity is just things coming off of material, like uranium salts, or many different kinds of elements and such. But they're coming off due to something happening within the atoms themselves. It's not that an atom reformed with a different atom to make another molecule. It's not some chemical process. It's inside the atom, something's happening. And that's why we're getting these strange sort of rays, these things emanating off of them. So it turns out there's kind of three main types of radiation, and they're essentially named in order. I think these are the Greek letter order, where alpha was the first kind of radiation that was discovered, that was from the uranium. And then you have beta and gamma, but alpha radiation is, well, as is shown in the picture here, we have this big nucleus and kind of showing a picture of all the different kinds of radiation that could come off of this nucleus. Right? If you have the nucleus is radioactive, then maybe you could have a chunk of that nucleus come off, and that chunk is a proton, 2 protons and 2 neutrons getting knocked off somehow or jumping off somehow. That's an alpha particle. And that's actually the same thing as the nuclei, or the nucleus of a helium atom. Helium is 2 protons, and you have the 2 neutrons. So it turns out alpha particles, or alpha radiation, is just helium nuclei. Beta radiation was the next one discovered, and that again turned out to be something we already sort of had an idea about, and that is just electrons. Generally fast-moving electrons, but beta radiation is just another way of saying these are electrons being emitted by radioactivity. And finally, we have gamma radiation. Gamma radiation is a broad term for any kind of electromagnetic radiation, so photons being given off. So if you have a radioactive nucleus, it can give off all these different kinds of things due to some processes happening within the nucleus there. And just to give you some more information or something else to think about, if you have a radioactive source, those different kinds of radiation will penetrate through different materials, some more, some less than others. And this is just an example of a couple of things. So the alpha radiation, or those helium nuclei, won't even really go through, say, a piece of paper. They get stopped by a piece of paper. Versus the beta radiation, those electrons will travel through the paper, but they'll get stopped by aluminum, or a metal generally. And then finally, the gamma radiation will go through the paper and the aluminum, but will get stopped up by lead. Okay, so what's happening with this radioactivity? Well, basically the most common type of radioactivity is due to radioactive decay. And decay is a term that basically means the nucleus of an atom is unstable in some way, and it will spontaneously start to break apart. So, say like in the last slide, well, we have kind of a similar picture here, where you have on the bottom left here we have a diagram. You start out with the nucleus on the left. That nucleus is unstable, and so it wants to break apart. And there's sort of these 3 routes that nucleus could go into. So if it goes through alpha decay, or alpha radiation, or it gives off that alpha radiation, it's this top one, and you have the original nucleus, but it gives off that helium nucleus, right? That chunk of 2 protons, 2 neutrons. There you go. That's one kind of radioactive decay. The other one, beta decay, it doesn't give off a proton or a neutron, but actually one of the neutrons is going to transform into a proton inside the nucleus, and you actually give off an electron as well. I believe you give off something else there too, we haven't talked about it. And finally, you might have something where it's just gamma radiation, but again, it's something usually where probably a neutron is transforming into a proton. So all of these are things where stuff inside the nucleus of the atom is sort of breaking down in one way or another. Maybe a part of it splits off, maybe one part of it just kind of decays into another thing, becomes something else. Oh yeah, and so a nice example of beta decay, right, we're giving off an electron, electron's the beta radiation, is the beta decay of carbon-14. So carbon-14, you start out with 6 protons and 8 neutrons in the nucleus. Right? 6 protons means it's carbon, 8 neutrons means it's an isotope of carbon. And if that beta decays, it generally will decay into nitrogen-14. And that will happen because one of those neutrons will decay and become a proton. So now you have 7 protons, 7 neutrons. So 7 protons, it's nitrogen. 7 neutrons, it's like the standard sort of nitrogen. And along with that, during that process, you get an electron that gets shot out of the nucleus. And there's your beta decay, or there's your beta radiation. So this is an example of beta decay. And as it turns out, there's a good amount of natural radioactivity. Most of the radioactivity you encounter in your lifetime is going to be naturally occurring radioactivity, and that's from things, radioactive elements in the atmosphere, it's from radioactivity happening within the Earth, and even within, stuff that you eat sometimes. Right, so we have elements, and some of them are unstable, like uranium, carbon-14. They're unstable, so they'll decay, and the nucleus will change, it'll become a different element. So when exactly any decay is going to happen, like say you're holding a carbon-14 atom, and you know it's going to decay at some point, again, quantum physics, this is a quantum object, a very, very small sort of thing. It basically says that you can't ever know exactly when it's going to decay. It's a probabilistic thing. So you could say it's likely to decay within this time frame. Or a more sort of macro scale look, a larger scale look at it, is if you have a whole bunch of the stuff, like not just one carbon-14 atom, but say you have several billion carbon-14 atoms and you have like a gram of it, right? Or you have trillions and trillions and trillions and you have more of it, right? So when you have that many together, it's still probabilistic of when anyone's going to decay, but on the whole, we could say that over this amount of time, about half of them will have decayed. So this is where the idea of half-life comes from, which is essentially a measure of how quickly or the rate at which a radioactive material will decay. So for the half-life is essentially just a time, it's the amount of time, and if you start out with a certain amount of a substance, say you have 1 kilogram of radium, then after one half-life, and the half-life is particular to that particular element, so radium's half-life is 1620 years, or 1620 years. After one half-life, you'll now have half of that radium you started with. And after another half-life, you're going to have half of that amount, so now a quarter of the original. So this graph is just showing if we started out all the way at the left, so 0 years from the start, right? This is where we're starting our clock here. We start out with a kilogram of radium. Since its half-life is 1620 years, you go 1620 years later, we're down to half a kilogram. You go another half-life up to 3,240 years, we're half of that amount now, right? So half a kilogram is a quarter of a kilogram. Go another half-life, length of that half-life, and you get half of that amount, right? So half of a fourth is an eighth. So each time you're cutting the amount down. Every time you go through a half-life, you're cutting down whatever amount was there in half. So be clear, that doesn't mean, as is shown in the graph here, that once I go through 2 half-lives, it's all gone. Right? You might be thinking that, well, you start with the whole, you take half away, you got half, you're going to take another half away the next time, and now you got nothing. Right? That's not how half-life works. It's every single time, at every single point, you're taking half of whatever is there. Right? So if I'm at a kilogram, go through 1 half-life period, I'm going down to half a kilogram. Right? Now I'm at half a kilogram. If I go through another half-life, it's half of that amount. So half of 1/2 of a kilogram, 1/4 of a kilogram. So, a little question about half-lives, and something that's going to help us maybe a little bit later, is say you start with carbon-14, some amount of carbon-14, and the half-life of carbon-14 is 5,730 years. So, how long will it take for whatever amount of carbon-14 you have to reduce to 1/16 of that amount? Take a second, pause, think about it. Hopefully you give yourself an answer and figure it out in a second. Alright, well, turns out it's deep. It's almost 23,000 years to get to 1/16 of the original amount. And again, it doesn't matter how much you start with. You could have started with a kilogram, you could have started with a gram, you could have started with 1,000 kilograms. Since it's decaying radioactively, it has its half-life, and every half-life, every amount of time that whatever that half-life is, you're cutting that amount down by half again. Right? So it doesn't matter what you started with, after 1 half-life you got half. After another half-life, you got 1/4. After another half-life, you got 1/8. And finally, after another half-life, you get a 16th, right? So you'll need to wait for 4 half-lives to have elapsed, for 4 time periods equal to the half-life of carbon-14 to elapse. And that turned out to be 4 times the half-life is 22,920 years. Quite a while. Okay, so keeping with this carbon-14 and also gives us a useful application of some of these, this idea of radioactivity and decay and half-life is what's known as radiocarbon dating. Right? And in general, it doesn't have to just be with carbon, it could be with any radioactive element that has a long half-life. You can do this sort of I think the general term is radiometric dating. But as it turns out, living organisms take in carbon, right? Whatever carbon's in the atmosphere. And that carbon is some ratio or some relative amount of carbon-12, the standard sort of carbon, 12 protons, 6 protons, 6 neutrons, carbon-12, or it's going to be this carbon-14, 6 protons still, it's got to still be carbon, but now 8 neutrons, right? So isotope of carbon. Carbon-12 is stable. It doesn't decay radioactively, right? So it doesn't have any half-life, it's not going to disappear, right? Whereas carbon-14, as I've been pointing out, is unstable, and so it will decay and actually becomes nitrogen. So while animals, or while organisms in general, are living and they're respirating and they're taking in carbon, then the carbon-14 that's in their body is slowly going to decay, but you're still taking in more carbon, so you kind of replenish that carbon-14 when the organism is alive. However, when it dies, the carbon-14 is continuing to decay, but the organism is no longer replenishing with new carbon-14. Right? So essentially, when an organism dies, it has a certain ratio of carbon-12 to carbon-14. Right? I don't remember or have it off the top of my head what the exact ratio is, but there's a certain amount of carbon-12, a certain amount of carbon-14, and since the carbon-12 is stable, it doesn't go away, but the carbon-14 slowly does. Right? So that amount of carbon-14 is slowly going away relative to the carbon-12. Which means that if you examine the organic elements, you can actually date organic materials based on how much carbon-12 is relative to how much carbon-14 there is. So the picture on the bottom here is essentially just showing if you started, 4 half-lives ago, 22,920 years ago, carbon-14 will have gone through 4 half-lives, and there'll be a 16th of whatever carbon-14 was left initially. So it's nice when a element or radioactive element has a long half-life like that. It makes it nicer because there's enough around for long enough that you can date back to fairly far back. It turns out that this is not just the ratio of carbon-12 to carbon-14 is not the only thing that gets used in radiocarbon dating, but that's kind of the easiest sort of thing to explain and understand. So I'll give you that one. So radioactivity and radioactive decay, those are examples of what we would call nuclear processes. This is kind of the segue into, more broadly speaking, nuclear physics. And essentially what makes a process nuclear is that changes happen within the atom, and generally within the nucleus of the atom. So these are changes that happen on a subatomic scale. So there are subatomic, I guess I've used that term a lot, but it basically just meant to say that there's a scale of the atom, which is already very, 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 very small, and changes where you have atoms rearranging and whatnot, that's mostly chemistry. But if you go within the atom, then we're talking about subatomic, and that's where we're getting into that nuclear scale in nuclear physics. So there's two sort of main types of nuclear processes, sometimes called nuclear reactions. One type is fusion, and fusion is essentially a combination, a combining of subatomic entities, subatomic particles, or you could also think about it as fusing them together. The other main type is fission, and fission is a type of nuclear process that breaks things apart. Radioactivity is actually kind of a subclass of fission, because radioactivity is things kind of falling apart in the nucleus. And as you might already know, both of these processes will release energy, and actually an incredible amount of energy. And that energy mainly comes in the form of gamma rays, meaning very high frequency electromagnetic radiation, very high frequency photons. It also comes in the form of the kinetic energy of those subatomic particles that are getting knocked out of the nucleus. Very fast moving subatomic particles, so they're carrying a bunch of energy in that motion itself, kinetic energy. Alright, so first let's talk about nuclear fusion, right? So fusing things together, meaning combining nuclei generally, protons and neutrons smashing together. So this process of smashing or combining nuclei together, again, will produce a lot of energy, and it also generally produce other subatomic particles as well. So one example of this process, or this kind of process, is if you take two isotopes of hydrogen, so in this bottom left diagram, on the left side of it, we have deuterium, which is essentially hydrogen with one neutron. So there's a proton, there's a neutron, deuterium. And you have tritium, which is, again, one proton, so still hydrogen, but now with two neutrons. Those are isotopes of hydrogen. If you smash those together, or just shoot them at each other fast enough somehow, then you can cause this fusion to happen where you fuse some of them together, and you actually create a helium nucleus, right, where you now have two protons and two neutrons. You also break off one of those extra neutrons, and it will kick off and become some kind of radiation. And you have this energy coming out. So that's one example of a nuclear fusion process. However, that's the sun, the thing that's powering the sun is nuclear fusion, and that's meaning that the inside of the core of the sun, the atoms and the nuclei that are there are moving so quickly, they're moving so fast, when they smash together, they get close enough that they can fuse together, and we get nuclear fusion. So I showed you this picture, I showed this picture to you all quite a while ago in this course as sort of a preview of nuclear processes, but kind of coming back to it now, where you can maybe understand a little bit more about it, in that in this sort of chain of reactions, you start out essentially with hydrogen nuclei being just a proton. So the little red guys are protons. And if you have two protons, you smash them together, then you can actually fuse them and form hydrogen 2, deuterium. So you have a proton and a neutron. And in that process, you get out, it looks like a positron, which is a positively charged electron, and this thing called a neutrino, which we don't really have time to talk that much about. So then you get that deuterium, and now there's still more hydrogen flying around there, more hydrogen nuclei, just protons flying around. You smash that together with another proton, then you fuse those together, you cause another fusion reaction, you get helium, but helium-3, so 2 protons and 1 neutron, it's not stable. Out of that process, you will have gotten this energy as gamma radiation. But if you have now these 2 helium-3 nuclei, each of them are unstable, so they'll only be around for a little while. They're going to decay in a little, if they sit around for too long. But if they smash together, then we finally get a stable helium atom, along with, well, 2 more protons, 2 more helium nuclei, or hydrogen nuclei. So this whole process is playing out in the sun, and each one of these steps, we're getting this energy coming out, right? Energy in the form of the kinetic energy of the positron of the neutrino, energy in the form of the gamma radiation, energy in the form of, well, the protons just being kicked out again as hydrogen nuclei and zooming off again. All this energy is coming out of each of these steps in this process, and that's what's powering the sun, essentially. So fusion is an essential process for life to exist on Earth. Most life. I guess under this, there's deep sea vents and whatnot where there's life around there that doesn't really rely on the sun, but for us, and for most life on Earth, we need this process. And I guess now that I've said that, those vents in the deep ocean actually also rely on nuclear processes too, so yeah, we don't really have time to talk about that. Okay, so the other process is nuclear fission. So instead of fusing things together, you're fissioning them, which means you're sort of breaking them apart. Now, the term never made that much sense to me, except if you think about it relative to fusion is fusing things, fission is the other one. Fission is breaking things apart. Again, radioactive decay is a form of nuclear fission because it's nuclei that are just falling apart in some way. So a more common type, or another type of fission is what would be called like a fission nuclear reaction, where you actually have, instead of a nucleus just decaying spontaneously, you have a nucleus and then you slam something else into it, but instead of fusing to that nucleus, it actually just breaks that nucleus apart. So in the bottom here are pictures of sort of the 2, I think, most common kinds of fission that happen in nuclear reactors. So a lot of nuclear reactors utilize uranium, and particularly uranium-235 as the fuel for that reaction, for those reactors. And they utilize fission because they essentially energize or somehow speed up neutrons and shoot neutrons into like a mass of that uranium. And so the neutrons will eventually hit one of those uranium nuclei, right? So the neutron comes in, hits that big uranium nuclei, breaks it apart, and so you get these other elements, other nuclei, as a product of that, and then you also get more neutrons coming out. But yeah, things colliding, breaking apart. So almost to the end here, it turns out that those processes and understanding this quantum world sort of leads us, or led us to formulate and kind of discover new forces that were at play in our world. So on our scale, and the things we talked about so far in this course are basically gravity and electromagnetism, right? So the gravitational force, the electromagnetic force. And on a large scale, even, down to like the size of viruses and cells and things like that, pretty small scale, these are essentially the only forces that are at play. And largely because those two forces are what we would call long-range forces, meaning if you have, say, like a source for an electromagnetic force, maybe a magnet, that force can be felt a long distance away from that magnet. And a long distance, when you're talking about sort of macro scale versus like the quantum scale, the subatomic scale, a large distance is, an inch is an incredibly large distance already. So trying to keep in mind that when I say like long range versus short range, we're talking about incredibly short distances versus like, I don't know, very short. So very short versus like unbelievably short. Right? So once you get all to that area of already very short, we're talking about the size of like cells and viruses and bacteria. Right? We're already on like the larger sort of scale. So electromagnetism and gravity are long-range forces, and the effect of them is felt far away. It turns out that these other forces that we've sort of been led to and discovered are what you would call short-range forces, meaning that the effect of those forces is only felt when you're very, very close to the source of that. Well, on our scale, it seems like a magnet might be a short-range force, right? Because if you have two magnets, you think about them, you're holding them out here, you bring them close together, and you don't really feel anything until they're pretty close together, right? So we have to extrapolate from that like when you're bringing them close together, say they're within an inch of each other, what we're talking about is still billions of times smaller than that. Right? So bringing them within an inch of each other, that's still fairly long range. And it turns out there's actually a force when there's this far apart too. It's just kind of weak, so you don't really feel it that much. Alternatively, like gravity, we know acts at a very large scale, right? Like, the moon's held to the Earth is held to the sun, those different things. So, my bad, I kind of forgot where to start with that. But, so the short range that we're talking about is ridiculously short, almost unimaginably short. We're talking about within the atom, scales within the atoms, and then within the constituents or the things that make up the atom. So it turns out that scale for these short-range forces is somewhere around the range of 10 to the minus 15 meters. So 1,000 trillionth of a meter. Unimaginably small. But with the advent of some new technology, experiments, our understanding of quantum physics and also relativity, which we'll talk about next time, some very genius experiments, we were actually able to probe those sort of scales. We were actually able to do things where you can kind of fiddle with stuff at that small scale, or be able to extrapolate from stuff at that small scale to get an idea that, yeah, there was something actually happening on those incredibly short scales. Okay, so we're going to end with just talking about what those new forces are. And again, I'm just giving you a very brief sort of overview of these forces. Right? So one is called the strong force, and very clever term, very clever naming. It's the strongest of the forces. So in the same sense, I think I've talked to you before about how electromagnetism is much, much stronger of a force, relatively speaking, than gravity is. And you can understand that by the fact that it's really only the electromagnetic forces between, say, the bottom of my shoe and the floor, it's the electrons in my shoe and the electrons on the shore, they're pushing against each other, that stop the whole entire Earth from pulling me in. Right? Because the entire Earth has this gravitational pull, is trying to pull me in. It's only the electrons in my shoe, at the bottom of my shoe basically, that are pushing against me to keep me up. And that's plenty. Right? So in that sense, the electromagnetic force is much, much stronger than the gravitational force. The strong force, it turns out, is something like 100 times stronger even than the electromagnetic force. It's the strongest of the forces. But again, it's only felt on a very, very short length scale. When things are very, very close together. And closer than you can hold your fingers together, essentially. You can't smash your fingers close enough together in order to get the atoms close enough together to start feeling a strong force. So, the strong force is responsible for holding things together at that subatomic scale. Right? So the strong force holds together the things that are composite at that level, meaning the things that are made up of even smaller things. As it turns out, protons and neutrons, largely we've talked about them as being kind of like a unit, a fundamental thing, but, well, they're actually made up of smaller things. Sorry. Those smaller things are called quarks. We're not really going to talk about those, but just know that they are smaller, and they're kind of what you build a proton out of. So there's a picture in the bottom left, which is essentially a picture of a proton that's made up of 3 quarks. Technically, they're called two up quarks and a down quark. A lot of weird terminology. Don't worry about it so much. But the proton is a composite thing. It's made up of smaller things, and it's the strong force that holds those things together to keep that being a proton. Similarly, the neutron is made up of smaller things, and again, it's the strong force that's holding those things together to form that neutron. And even further, there's a bunch of other things that are still fairly fundamental in our world that are held together. They're like essentially bundles of quarks. So there's things like pions and kaons and all crazy manner of things, and those things are again made up of smaller stuff, and those held together by the strong force, right? So that's one of the things the strong force does. The other thing that it does is essentially hold nuclei together. So not only is it holding the things that are inside the proton together to keep that being a proton, it's also going to hold a proton and a neutron together to form a nucleus. Right? So the picture here, we have that helium nucleus, right? It's made up of 4 nucleons, 2 protons, 2 neutrons. We could call it an alpha particle, just because of historical reasons and what I talked about earlier, right? But the reason that those things are held together, if you ever thought about it beforehand, it doesn't really make much sense in terms of like gravitational force and electromagnetic force, right? The things are so incredibly small that there's almost no mass there that the gravitational force between them is non-existent. So it's not gravity holding them together. And beyond that, there's 2 protons there. So there's 2 positively charged things there, right? So the electromagnetic force would actually want to repel them, right? You have like charges, or 2 like charges, they want to push each other apart. Right? So if you thought about a nucleus beforehand in any detail, you would think, that doesn't make any sense. Why are they even held together? Well, as it turns out, it is the strong force that is holding those things together. And again, it only works at those very, very small scales. So within, say, the nucleus of an atom itself. All right, so finally, we're going to talk about the last one of these, or the other short-range force. It's called the weak force. And again, very clever naming scheme. It's called the weak force because it is relatively weak compared to most of the other fundamental forces. It turns out it's still much stronger than gravity. Gravity as a force is just incredibly weak. So, compared to, say, the electromagnetic force or electromagnetism, I think I have the numbers correct here. The weak force is 100 billion times weaker than the electromagnetic force. And again, remember, the electromagnetic force is still weaker than the strong force. So essentially the order is strong force, electromagnetic force, weak force, gravity. Right? So gravity, it turns out, is still far weaker than the weak force. And I think I have this correct. The weak force is roughly, 10 trillion, so that's 10 with 25 zeros, times stronger than gravity. So again, it's weak relative to the strong nuclear force, but it's still much stronger than gravity. What the weak force actually does is very difficult to explain conceptually. It's difficult to explain in general, actually. But at this level, there's not really much I can say about it other than to give an example of what it does, or a place where it is sort of part, or what it's part of, and yeah, maybe something else. So an example of where the weak force is in play, or where the weak force is acting, is in beta decay. And I think in other decay processes, some other decay processes too, but beta decay specifically is essentially handled by the weak force. When beta decay happens, it's because of the weak force. And another thing I could say is that this neutrino, this subatomic particle, it's a fundamental particle, it's not made up of any other things as far as we can tell. That thing in itself is very closely linked to the weak force. It's sort of interwoven with the weak force. And so basically whenever you have a nuclear process or some kind of nuclear reaction and there are neutrinos involved, neutrinos coming out, neutrinos going in, that's pretty good indication that is a weak force interaction. There's a weak interaction happening there. So yes, all right, so radioactive beta decay, like that beta decay of carbon-14, is a weak process. So the weak force is what causes this beta decay to happen. In that beta decay, we go from carbon-14 to nitrogen, but we also get out this electron and an anti-neutrino. It's still a neutrino. It's anti and regular neutrino, basically the same thing as far as we're concerned. So so it's weak force is responsible for why beta decay happens, and whenever you see a neutrino, basically that's a weak interaction. There's a weak force going on there. Yeah, that is all I have then for our quantum and nuclear physics lecture. Again, most of this is very abstract sort of concepts, difficult to understand and to kind of take in internally, really internalize these ideas. I'm not expecting you to be an expert on any of the stuff that I've told you about, right? This is to give you an overview, and just like this course is in general, for the most part, is to give you an understanding of what the different aspects of physics are. So now we're in the modern realm of physics, quantum physics, nuclear physics, and relativity next week. And some of the things are fairly simple, half-life, not that tricky of a thing to understand. Other things, rather complicated. So yeah, so take what you can and hopefully get something. All right, well, have a good night. I'll see you next time.